Today, what I'm going to do is I'm going to give you an overview of the research computing platform services at UCL and how we try to keep those uniform so that users can move between them with a minimum of effort and fuss. So I'm going to talk about Grace, Legion, the software stack we deploy in both of those, and talk about some of our plans for the future in terms of upgrading and better supporting our researchers. So if you go back about a year and a half ago, the main research computing service at UCL is a service called Legion. It is, as Claire has said, the original research computing service at UCL. And has been in service since about 2007. It's undergone a process of continual upgrades. So every couple of years we put in some new hardware, we replace some bits. So as of now, it's kind of a kind of ship of Theseus type thing where, although it's called Legion, almost none of the original system is in service. Except, I think, for some of the core networking technology, which is 1 gigabit Ethernet, and therefore, although stated out at the time, is now kind of out of date and creaking a bit. So just to demonstrate how much of a mess it is, currently there are 8 different node types in Legion. This pie chart shows a breakdown of the node types per core, of which the most common are the newest sets, which is the U nodes here. We give them letters to identify the node types. And there's a fairly large chunk here of X, Y, and Z, which are now the oldest nodes in Legion. Some of the nodes have InfiniBand between them, so that you can run MPI parallel jobs across groups of the nodes. Some of them don't. Some have various kinds of accelerators, so GPUs or Intel mic cards. Some of them don't. And this messy state is somewhat exacerbated by the fact that we have a system where PIs can pay, principal investigators, can pay to put hardware into Legion for their use, which is then used in priority by them, but other people can use when it's not being used. And they pick the hardware they want, so again, that increases the messiness a little bit. As I said, Legion is very bitty, and it's actually spread about the campus a little bit as well. So it's not very suitable for doing large parallel jobs. So 3-4 years ago, we bought into a service at Southampton called Iridus 3. And Iridus 3 was a large parallel machine, and we made a lot of use of that. So what's the difference between the kind of jobs we can run on Iridus and the kind of jobs we could run on Legion? Well, Iridus can run parallel jobs, so by that I mean a large single piece of work takes many compute nodes running at the same time. It's very sensitive to network performance, so if you remember that 1 gigabit Ethernet network in Legion, it kind of makes it not suitable. And that tends to be things like physical sciences, so primarily chemistry and physics and engineering. On Legion, we run much smaller jobs, so what we term high throughput computing. So you run lots, tens of thousands of jobs on lots of independent data, and because there's lots of bits of data, it's very high in I/O. And currently that's dominated by biosciences and again physics, because physicists just get more out of all the machines all the time. In future, we hope to expand into digital humanities because we have an ongoing goal of conquering the whole of UCL and all its research output. To give you an example of the scale of that number of jobs, so remember we said that on Grace in a month there was about 3,800 jobs. In the same period, Legion ran 750,000, right, but they're very much smaller. So if you're like me, you prefer to look at things in terms of pictures, so to explain the same thing pretty much again. With a parallel job, you have one large chunk of input data, you have a bunch of identical processes which operate on it at the same time, coordinating with each other over a network. At the end, you get your output out. Pretty much all programs look like that. There might be some steps in between, but that's pretty much how they look. The important thing to note is that these programs all have to run at the same time in order to get their work done, right? So you have to block out a big chunk of the machine. For high throughput, on the other hand, you tend to have one program run many times on different sets of data. And these tasks can run independently, they can run out of order, they can run in any order. You can run this task on the same node as this one after it's finished, if that's how things work out. And this is the kind of work we do on Legion. So, in about summer 2014, Southampton gave us some rather bad news. And that was that the next summer, in 2015, they planned to retire Iridus. And so we panicked a little bit, because this would mean we're going to lose about 71 teraflops of compute capacity. So what do I mean by that? So one flop, or one flops, is one floating point operation per second. Right? So that's one mathematical operation on 2 floating point numbers. 1,000 times that is a kiloflop. 1,000 times that, mega. 1,000 again, giga. 1,000 again, tera. Right? So that's a lot of compute power we're losing. But also, because of the way Legion is built, we're going to lose that ability to run large parallel jobs. And we couldn't negotiate with Southampton either, because not only were they retiring Eridus, but they wanted to retire the building it was in. They wanted to put a bulldozer through it in summer 2015. So we're in a bit of trouble. At the same time, we had some of the original Legion hardware still in service. And we wanted to retire that because, well, I've said 7 years old there, but it was 7 years when we wanted to retire that. It's about 9 years it would have been now. And that was old, it was failing, it was out of warranty, it was massively energy inefficient. It had an InfiniBand network, but that had actually failed, so it could only run jobs on one node. And all in all, the capacity we're losing there was another 20 teraflops. So all in all, we're losing about 91 teraflops worth of compute, which is pretty hazardous to our researchers in terms of completing their work. Luckily, some clever work by Claire and her predecessor Gavin meant that there's been some scrimping and saving, and over 2 financial years we had £1.5 million to spend, so that was good. So we went out to tender, and we asked the vendors for a machine to effectively replace the Eridus compute. So we wanted a large parallel machine with a ubiquitous fast network, so we could run parallel jobs over the entire machine. And in the end, our friends at OCF won the contract, and we put into place Grace. So Grace went into service on the 2nd of December. It's a completely new service, distinct from Legion, they're not linked in any way. All of its nodes are connected by a ubiquitous InfiniBand network running 40 gigabits, so that's 40 times the speed that the 1 gigabit network in Legion is running at. But also it's extremely low latency, which is important for running MPI jobs across the machine. It's also the only network that users ever see. There actually is a sort of secret Ethernet network for management, because sadly the hardware is not modern enough, not advanced enough yet that you can boot it off the InfiniBand network. But all traffic that the users do goes over the InfiniBand network. So that includes file transfers, reading and writing data, MPI commands, all that stuff. And we also built in upgradability, because we looked at the example of Legion, and with Legion, every time I want to add something to it, we have to keep sort of duct taping bits on the side, which is not very elegant. So the core network infrastructure for Grace is designed to be expanded to up to 2 times its original size. So at the end, we had to decide whether we'd actually achieved our goal of replacing the compute capacity that we'd lost. And if you recall, we lost 91 teraflops of sustained compute, and we benchmarked Grace with the LIMPAC benchmark, and we've got 181 teraflops. So we've effectively doubled the compute capacity available for large parallel jobs at UCL. The other goal, of course, was to move things off the Legion service, because we had a small number of parallel jobs running on Legion. And so after Grace went into service, what we have here is 2 graphs. The text is slightly small, but it's not that important. What we have here is a graph for the jobs you run on Legion and jobs run on Grace in the same month. Going from left to right, we have increasing job size in terms of number of cores. And the red bars are the important bars here, because they're the amount of compute time used. So if you look on Legion, the usage is predominantly on the lower core count jobs. And on Grace, it's predominantly up here around 512 to 1,024 cores. So we also succeeded there. One of the reasons, we put the Grace service into production pretty quickly. So we completed the tender in, I think, May. We gave the bids to OCF, and we had the hardware in place sort of August, September, and we put it into production in December. So that's pretty short for one of our projects. And one of the reasons we were able to do this is because at the same time we were going through all the procurement process, and Lenovo were building the servers, and OCF were doing their integrations, we were busy building the software stack that the users would actually interact with. And this is because we were able to do this because, again, in 2014, we decided we really wanted to do a refresh of the software we make available on our services to users. The software stack then was very long in the tooth. It had a fairly ancient, some might say, kind of archaeological version of Linux on it. It had management software bought in from a vendor that we had to pay licenses for. And we really didn't want to move to a situation where we had 2 services that we had to manage in different ways and give different experiences to the users. So we decided to do an upgrade to the Legion software stack, and to mandate that the new service, Grace, would have to run that software stack as well. So while the procurement was being done, my team and Tom's team were very busily working away, building up the application stack for the 2 services. So they had a common software stack. We based it on Red Hat Enterprise Linux, and we chose that because UCL has a license for it, which allows us to do that. We built it based on Red Hat Enterprise Linux 7 because we worried that in future we might not have a chance to upgrade it as fast as we'd like, so we had to be a little bit ahead of the curve. We use a scheduler called Son of Grid Engine, which is an open source variant of 7 Grid Engine. And we use a package called environment modules to allow users to pick which applications they want to use. On top of that, my team provide a common set of compilers, which a compiler is a program which lets you take the source code that you've written and turn it into machine code, so you can run it on the machine. A set of libraries so that researchers don't have to write all their programs from scratch, so we've got common things like FFTW and LAPACK and BLAST, and various implementations thereof. But also, importantly, we have an extremely large set of supported applications, with the aim that when a user gets an account and sits down and logs in for the first time, it is quite likely that the software they need to use to do their research is already there, and they just need to put their data in, submit a job, get their results, publish a paper, take it to the supervisor and go, yes, look, I'm successful. If you are a new user and you need an application that's not on there, it's my team's job to put it on there for you, assuming that there are licenses for it. And from our point of view, from the management side point of view, we've really tried to make sure everything you do is automated. So we script up application builds. The systems team use tools like Puppet to orchestrate the software on their end. We use an open source management package to manage the cluster called XCAT, which exceedingly conveniently is the same one that OCF uses by default, so that wasn't a decision that wasn't a factor in why we chose it. And our aim really is that it's easy for the users to move between the services as well. So if you're running a program at a small scale on Legion, and you suddenly realize you need to run 1,024 cores, you can get a Grace account, just copy your application data over, and everything will just work. I'm sorry, those URLs are fairly unreadable on the screen. We are quite keen that we give our work back to the community, so all of the work my team has done in automating application builds is available publicly under an open source license on GitHub. The URLs are there, but they'll hopefully be on the slides, which should be available on the web later. But the goal with this really is that if you are UCL and you're in a small department with a very small cluster, you can take those scripts and install the applications yourself and do your testing there before you move on to our services. Or even if you're running Linux on your desktop, you can do the applications on your desktop. So now we have 2 HPC services. And what we really want to do as a result of that is, rather than having gaps in our service provision, what we will do is we'll upgrade them alternately, effectively. So the next time we do a big deployment, it will be to upgrade Legion. And when Legion was originally commissioned, if you recall, it was UCL's original HPC service, it was intended to be a general purpose machine. And so there were some architectural decisions which were taken then towards that goal, which make it slightly unsuitable for high throughput computing, which is what it does now. So what we really want to do is fix these issues. The worst one by far is the I/O problem caused by that network. So transferring files between storage and compute nodes on Legion is incredibly slow compared to Grace. And so we also want to retire some of the old hardware. So remember I showed you the XYZ nodes, which are about half the machine. Those are also coming out of warranty, are incredibly old, incredibly energy inefficient, and so we want to replace those. So our next planned upgrade is upgrading Legion for data-intensive, as we call it, computing, targeting biosciences and the digital humanities. We're not entirely sure what all of this upgrade will comprise, but we're going to get rid of those old compute nodes. We're going to replace the core network. One of the things we want to do is start doing local mirrors of commonly used data sets, so both biosciences and digital humanities have large data sets that are used by lots of people, so we want to have local mirrors of them rather than pulling them off of the internet. And of course, whatever is the most up-to-date version of our software stack. And finally, I am only interim platform services team leader at the moment, and I'm quite keen to point out that any success is entirely due to my excellent staff. So I'd like to thank Dr. Ian Kirker, Heather Kelly, and Brian Alston, who are my team and have worked on the application side of things. Thomas Jones, Luke Sudbury, William Hay, who are our systems team, and some of them are here. You might see Tom starring in a video later today. Colin Bylong from Networks, who gave us some excellent support in terms of the networking. We had incredibly great academic support in this project, with oversight from Professors Dario Alfi and Dr. Javier Herrero, apologies. And they will in fact be judging the poster competition later. And Dr. Jörg Sassmanhausen from chemistry as well provides some excellent technical input. And finally, we had 2 excellent project managers Mike Atkins and Greg Dyer. And of course, our wonderful friends at Lenovo and OCF, and I've put some of the names up there, but it's by no means an exhaustive list. So thank you all for that. So my next duty is to introduce the next speaker. He has an incredibly long list of professional achievements, so I'm not going to list them all here. But currently, he is, amongst other things, the Tate Professor of Mathematical Physics at Edinburgh University. He's the chairman of EPCC, which means he's been involved in national resources like HPCX, Hector, and Archer. He's the vice principal for HPC at the University of Edinburgh, and he's also a trustee of the Alan Turing Institute, which is starting up just down the road where the British Library is. Somehow, in that time, he finds the time to also do some physics and works on quantum chromodynamics, amongst other things. And by far and away, the most important of his achievements to me, but not to everyone else, is that he's also my father. I'd like to introduce Professor Richard Kenway.